Okay, so now we are doing some practice questions for Unit 2, which is the force, the laws of Newton's, and gravity and friction. We are on an AP Physics website. We try to understand some of these questions, and this will help you to get ready for your midterm exam. Okay. Okay, now here's the first one. It says, this is the wall. There's something you connecting to wall. So the person is cleaning the wall by pushing a brush against the wall, as shown in this figure. The person pushing the brush upward with an increasing speed. What does it mean? It's pushing upward with an increasing speed. What do you learn from this little tiny sentence? Jaden? It says you're pushing the brush upward with an increasing speed. What this sentence means?
So the force is increasing.
No, force is not increasing. Speed is increasing. That means there is a force.
There's an acceleration.
Exactly. That means there is an acceleration. That means there is a force. And that's the meaning of it. Now it says, which one of the free body diagrams best represents the motion described in this one? Okay, so before we do, you push. When you push, you are pushing against the wall. So wall is going to push against you. So this one will have a normal force perpendicular to the wall to the left. It has a mass, so there is a force downward. Now it says you're pushing it with increasing speed upward. That means there is a force horizontally on parallel to the wall upward as well. So there is one force perpendicular to the left, one force down, one force upward. Is there any force toward the ball?
He's pushing the brush against the wall. So
Yeah. Is there any force?
Yeah.
To the right side?
Yes.
What does it mean? Well, you are pushing this object against to the right side, but does the object moves to the right side?
Oh, no.
It doesn't. So that means the only thing you do by pushing it to the right side, you're creating a normal force where the normal force is acting on the brush and it's to the left. Okay, so which one do you think is the answer? A, B, C, D, or E?
Is there friction?
It's a good point. Is there any friction here? Does it say anything? Does it say the friction? Ignore the friction. The person is pushing. No, it doesn't say anything. So feel free to assume that friction exists as well. But then, which direction the friction would be?
In the opposite direction of the
Motion.
So down.
So if it's moving up, then it has a friction downward. Okay. Now the question is, which one is? Now it has to tell us. How do we push this? And look at the handle, right? The hand is pushing this, right? So that means I suppose I can assume that it's pushing along the arm, which is tilted, an angle. So there's two components, vertical and horizontal here, right? Or you can say there is a force in this angle. Then there is a weight and a friction downward, and then there is a normal force to the left. This force, which arm is exerting, is going to break into two components. Now, if I had to draw such a diagram, I prefer, there's two steps in it. Okay, let me go to this one so I can draw and so you can see. Okay, so this is the wall. Can I write? Oh God, what is happening? My pen is lost signal to my iPad. Let me stop recording. Okay, so this is the wall, and this is the brush. So the brush itself has a mass, so there is a force downward. Then you're pushing it in this direction, technically, right? So you're pushing it with this force in this direction, and that basically breaks into two components, right? One upward, one downward. So this push to the right side will create a normal force for us, a normal force which is this way. And then because it's moving up, then the normal force is going to create a friction downward. So friction. So there is a force of gravity, there's a friction in this way where the friction is mu dot n. N is actually, if I know what is this angle, let's say this angle is theta, and so technically this angle is theta. So this becomes, if this is the external force, this component is adjacent, so they become f cosine of theta. This becomes f sine of theta. So n would be equal to f sine of theta. Okay, and then you will have what else? You will have the f cosine of theta. This is f external, minus f of g minus f of mu is going to be, oh, in this case, it's not going to be 0 because it says, the question says it's accelerating upward, right? So this would be technically the equations. But if we have to draw this free body diagram based on the components, then you would say, I'm going to draw it this way. That's my object in the middle. Then I will have a force, two forces downward like this. I will have a normal force to the left. I will have a component of the F to the right, and I will have a component of F to the up. So that would be all the forces. Or you might actually say, okay, I want to draw it this way. So there's one force here like this, and then there is the mg from outside like this. Now, this is not complete because there's a wall, and then the wall is going to apply a normal force to the left, but this component is going to break it into two components for us, right? Now, when you look at this assignment, these questions, you don't see this one. That means he's actually looking for the pure forces and not the components. So you have to get rid of this component, and consider this one as your free body diagram. So this is the kind of free body diagram the question is looking for. Right. So let me just go back to the diagram, right? So you don't have forces in all direction. You have a force in this direction, and you have a force to the left, you have a force down. Now the question is it D or E? Well, you have to look at this one. What is the angle, do you think, is the angle? Looks like E is more vertically pushing at the wall than D. I'll go with a D. Okay? Here's the next question. What this question says. Okay, so it gives you the free body diagram. I prefer if it didn't. It says that you have a block of mass M is initially moving on a rough horizontal surface, as it's shown. Figure 2 shows the four forces acting on the block. Which of the following best describes the motion of the block at the moment shown in two figures. Okay, now looking at this one, n and mg are equal. What does it mean, Jason?
It's not moving on the y-axis.
Right, so it's not going up and down. There's no acceleration vertically. But now the small f, is much larger than large F. What is large F? Is the external force which is causing this object to move to the right.
Yeah.
What is the lower F? Is the force of friction, which is created because of the normal force. Now this one says the lower F is larger than uppercase F. What does it mean?
Slowing down. Or
exactly, decelerating.
Mhm.
Okay, so which direction the object is moving? According to the left, figure 1, to the right. But which direction is the direction of acceleration?
Left.
To the left. Okay, now we'll read the answer. So the block is moving to the right and speeding up. No, it doesn't. The block is moving to the right and constant speed. No. If the speed was constant, this lower f and uppercase F should have been exactly the same size. The block is moving to the right and slowing down. The block is moving to the left, right. So D and E is not the answer because it's not moving to the left. So C would be the answer, right? Slowing down and it's moving to the right. Let's just do another one. What is this? You have a block, a wooden block is placed on a rough surface. The surface starts horizontal and one end is then raised to that the angle of the surface makes horizontal gradually increase until it's theta. So you slowly bring it up until it reaches theta. The block begins to move down the surface at some angle. Okay. First of all, does it say anywhere if there is a friction?
It's a rough surface.
Oh, it says a rough surface. Does it say it? Where does it say that there is a friction? Right here. So it's on a rough surface. So there is a friction. We don't know how much, but there is a little friction. Now, if I had to solve this problem, how much would be how much would be when this object starts moving? That's a better way to put it, right? So let me just draw it and then show you what I mean. So this is the object. At some unknown theta, this starts coasting with a constant speed down. That means this force mg and this n and this little tiny friction here, they reach a point where there is basically the force which is created in the right side is exactly equal to this friction and it causes it to move. Okay, let's just break this mg to two components. If I know this is theta, that means this is theta. That means this vertical component, which is equal to n, is equal to mg cosine of theta. Agree? And it's not going up and down with respect to the surface, so it's equal to 0. So n is equal to mg cosine theta. F of f is mu dot n, which becomes mu mg cosine theta. Okay, so that's the friction. If I need this object to slide down, I need a force, which when I subtract it from f of f, this becomes just a little higher than 0, right? So if it's not 0, then it accelerates downward. And that's exactly what we need. So the minimum amount is when it's exactly equal. When it's exactly equal, then it's enough to basically start sliding. And the reason is we know that the static friction is larger than kinetic friction. So if it's equal to static friction, it starts starts moving, but then suddenly, because the friction is now kinetic friction is a little less, and so it's accelerating downward. Okay, now, how much is this component, downward component? The downward component is mg sine of theta. So mg sine of theta minus mu mg cosine of theta. If it's equal to 0, then it starts moving right away. Okay, let's take this one and solve it, right? Mg sine of theta, mg sine of theta minus mu mg cosine theta equal to 0. That's mg sine theta equal to mu mg cosine theta. And look what happened. M cancels M, G cancels G. You will get mu is equal to sine theta divided by cosine theta, which is tangent theta. Now, I want you to remember this. This is the friction. The friction of the surface is equal to tangent of theta. So theta, the angle, is technically tangent inverse of mu s. That means at some particular theta, this object starts sliding down. Good? Now let's go back to the question and review it. Since there is no frictional force on the block, now it says the block is sliding down, and it already says it's a rough surface, so there is coefficient of friction. There is a motion. If there is a motion, so there is friction force. And also it says here, it begins to move downward the surface. Okay, now let's read the second one. Gravitational force is equal to the friction force. Is it? No. Friction is not equal to gravity. Gravity is mg. It's not equal to mg. The friction is actually equal to mg, if you like, it's mg sine of theta. Okay, the component of the gravitational force along the surface is greater than the frictional force. This could be true. If it's accelerating, then yes, definitely this is true. If it's exactly equal, then it's coasting down, but it's not accelerating, but it's still moving. It's very likely that it's accelerating. What about this? The normal force is equal to gravitational force. Now that's not true, because the normal force was mg cosine theta. It's the component of the vertical component of the mg becomes the normal force. The components of the normal force along the surface is greater than the gravitational force. No, the components of the normal force is not going to cause this object to move at all. So technically, the only answer which is meaningful would be C. Good? How about this one? You read and you tell me what happens. So you have some coffee filters, you drop them. They're not point-like objects, so there will be air resistance against them. Now it says that this air resistance, this drag force, is equal to minus B times V, means the drag force increases or decreases with velocity. The higher is the velocity, the higher is the drag force in the opposite direction to velocity. That's the meaning of this equation. It's linearly changing with velocity. B is a positive constant relative to the surface area and the shape of the coffee filters. Now, the teacher demonstrates how the value of the constant B can be determined by releasing coffee filters from rest and having them fall downward. A motion detector as shown here. They have a motion detector here. They fall, and this motion detector detects how fast they are falling. Now the students repeat the activity and uses the motion detector to measure the position, velocity, and acceleration of different coffee filters as they fall. which of the following would provide the data needed to determine the constant b? Okay, so first, tell me why this object is falling.
Gravity.
Gravity. So that means technically this object, there's a gravity on it, F g, which is equal to m times g, and now there is a drag force here, and this drag force is technically b times v. There's a negative, but that negative, I already put it into this direction. If I consider this direction as positive, this direction as negative, then this becomes minus bv. This, if I put this as a vector, this becomes minus mg in the z direction, and this one would be at z direction. Okay. If on the other hand, if I consider this direction as positive, this direction as negative, then I can put a negative down there. But it's easier if I go with this positive upward. Okay, now if the object is falling and reaching this terminal velocity, then always you have the f of d minus f of g equal to ma. If it reaches terminal velocity, that means acceleration is 0. And so you can easily say that f of d would be equal to f of g. Now, why this is important? Because you can calculate this f of g because it's technically m and g, right? And if you plot, okay, so what are you measuring? You're measuring position, you're measuring velocity, and you're measuring acceleration. So acceleration, so let's just do it this way. Let's say that it's not reaching that terminal velocity, so the f of d minus f of g would give you m times a. So this is b times velocity v. This one is minus mg, and this is equal to ma. bv would be equal to, take a factor of m, and so this becomes a minus plus g. So if you are measuring the acceleration, that means you're measuring this quantity. And if you're measuring the velocity, that means you're measuring this quantity, right? And so you will have a data, you have a table, which is technically velocity versus a plus g. If you plot them against each other, velocity, let's say, versus a plus g, what do you get? You will get the ratio of a plus g by velocity, which is, by the way, is b divided by m, which in average, you can know what is the mass of these filters in average, if you know it. And so the slope of this diagram from the horizontal, this theta, would be related to this quantity, would be related to the b and the mass in average, the mass of the filters. Okay, now let's read the answers and tell me which one do you think makes sense. Okay, the first one says, cut coffee filters into different shapes of the same surface area and measure the terminal velocity of the coffee filter. Okay, so what are you trying to understand? B, right? So if you cut the coffee filters, what is changing here? You're changing the mass of the coffee filters. And if you let them reach a terminal velocity, then they will reach terminal velocity at different velocities. Assuming that the b is a constant, then Okay, that sounds possible. What about the next one? Vary the diameter of the coffee filter and measure the final velocity of the coffee filter. Vary this, let's see, let's read the C. Vary the starting height of the coffee filter and measure the final velocity of the coffee filter. What are we looking for? Which of the following would provide the data needed to determine the value of the B? And then stack multiple coffee filters in order to vary the weight of the system without changing the surface area, and then measure the terminal velocity of the coffee filter. How about this last one? Okay, so why the last one is more interesting? Because go back to this. It relies on terminal velocity. It says you have the f of d, you have the f of g, and you want the terminal velocity to reach. So that means acceleration is 0. So from left side, you have bv. From right side, you have mg. So if you had objects with different mass, right? So then you will have definitely you have mg, which is different for different number of filters, and then the terminal velocity would be different. So you will get some numbers like this. And so a best fit like this can give you the slope here. And the slope here is technically mg by velocity will give you the constant b. So the slope here will give you the slope b. Does that make sense? So you're varying the mass, and then you will get different terminal velocity. And so the slope of that uh, diagram will give you the constant. Okay, this one is easy. You read it and tell me what do you think. Good. So it has a constant velocity in the x direction. Then when it reaches the origin, then there is a constant force vertically in the positive direction. So it's upward. So it's going to accelerate upward. So it was moving with a constant speed velocity in the right direction. Now there is an acceleration upward. What happened? From the origin, slowly drift away from the x-axis and follows a quadratic equation, perhaps. Or at least, in this case, you can say it's going to bend up. Okay, so it's not going to be like this. It's not going to be like this. Why not? This one is moving toward y direction, and then there's acceleration toward x direction. So this number D is not right. Number B is the same. It's technically moving on a straight line in both direction, x and y. And then there's an acceleration toward x. So again, this is not right. So between C and between A, now we have to decide which one would be the shape.
I think C.
Why C and not Y and not A?
Because it's moving with constant velocity. It's
Okay,
constant force in the y direction.
constant force. So what does it do? A constant force creates a constant acceleration.
Mhm.
If you have a constant acceleration, then let's just go backward and look at the equation. So it says constant acceleration. right? So A is constant. What is A? Is d velocity by dt is going to be constant. That means velocity is a constant multiplied by time. So that would be technically the velocity change. And so if you have the velocity change like this, dx by dt is going to be the velocity. It's going to be a dot t. Solve this one for x, and then x would be some half at2 plus v0t. So the function which shows you the x as a function of time would be quadratic. X would be proportional to t to the power of 2. Good? Now, how do we plot this equation? X is equal to some numbers, like 2 times t squared, or 1 times t squared. Okay, so here is my diagram. So this is my t, this is my x, and this says first of all, t is positive, so I'm only limited to the right side. And so when t is equal to 1, x is equal to 1. So t1, x is 1. When t is 2, x is 4. So when I choose 2, then it would be 4. When I use 3, then it would be 9. Oh, goes completely outside of my thing. But when you connect them, you can see that this goes really far up like here. So that means it has to be like this. Okay, so technically it's a parabola. It's like this. And so now look at these two equations. Which one looks like a parabola? Now this one, C, looks like a quarter of a circle, right? This one, on the other hand, is more like a parabola. Now, I'm not sure if parabola is and the circles are the same, so I'm going to plot it by machine. It's much easier for me, right? So I would say y is equal to x to the power of 2. That's parabola. And if x is positive, I would basically put here bracket, and I would say x is larger than 0. Right. So this becomes what we have. It's similar to which one? It's more like A than C. Right. I think it's more like the A rather than C. C is more, rounded. It's not like, it's more like a half circle or 1/4 of a circle rather than parabola. Good? Okay, so let's just do another question. Okay, you read this question. I want to also do some other examples. I want to find some good examples relevant to what we want to do tomorrow. So a ball is thrown straight down from the top of a building with a speed greater than its terminal velocity vt. Which of the following graph best describe the velocity, the speed of the ball as a function of time while it falls to the ground? So initially, it has a velocity which is higher than terminal velocity. What does it mean? It cannot go faster than terminal velocity, so it has to slow down, right? Does that make sense? So if it was slower than terminal velocity, then its velocity would have increased to reach the terminal velocity. But now it's already moving faster than terminal velocity. Now you have to get rid of some of these. So there's an acceleration in the opposite direction, in upward. So it slows down initially, and then it becomes constant. So how do we show constant on a velocity x? What is x? X is by distance, right? Velocity versus x. It's not velocity versus time, it's velocity versus x. I think it's funny because it says straight down and then it uses x quantity. I think it made a mistake. The person who created this question needed to put time on the x-axis, not x, because technically it's falling down. X is 0, or it's the same, doesn't change. But what is actually changing is the position y and also the velocity. But usually nobody plots the velocity versus x or y. We plot velocity versus time, and also it here says represents which of the graph shows the function with respect to the time. So I'm kind of confident that the x-axis must be time, not x. Okay, initially is faster, so it has to go down with time. So A shows you that the speed goes up. No, that's not the case. B, the speed goes up. That's not the case. And E, also the speed goes up. So the only two answers which are perhaps acceptable are C or D. Now, here's the thing. What is the terminal velocity? This dashed line, right? And if it's moving faster than the speed of the terminal speed, it has to be above the terminal speed, but eventually it has to reach the terminal speed. And so D cannot be the answer. The only one which is meaningful is starts from higher than terminal velocity, but it goes down and reaches the terminal velocity. So that's the only meaningful answer. The rest of them are, you don't even need to worry about the curve here. Okay. Now that we got to this point, I want to go back and do a little review on, what is it here? Things that we talked here. Now, I want to make sure that you remember that what is a force? What is a force? It's just a push or a pull. It might be contact or it might be field, means no contact. But still, it's a push or pull. There's no other ways to describe force. It's a push or a pull, which may causes change in the position, causes acceleration. We use Newton as a unit for it. And the net force is the sum of all the forces on one object. So if you have two forces to the left and to the right, then the net force in the x direction becomes, in this case, the F in the right side minus F in to the left side. There are four fundamental forces in the nature, which we need to make sure we know them. Friction is also a force, normal force is also a force, but these are not fundamental forces. The friction is electromagnetic force between the two surfaces, and the normal force is technically a third Newton's law reaction force. You push against the surface and the surface is pushing you back. These four fundamental forces, you need to know and make sense of them. Gravity is easy to understand. There's mass. Mass causes attraction between the massive object. There is a nuclear forces inside the nucleus, one weak nuclear force, which is involved in radioactivity and radioactive decay. And then you have nuclear strong force, which is the force connecting the protons to protons and protons to neutrons. that keeps the nucleus connected together. If this strong nuclear force didn't exist, then we shouldn't have anything heavier than hydrogen. So you and I, made of carbon and oxygen mostly, should not exist. So this strong force, the evidence for the existence of this force is we, everyone, right? Everything has carbon, oxygen, heavy elements, so because the protons can form heavier elements in the chemical table. What else? Oh, here we talk about the friction. Friction is a contact force and is also related to this idea that whenever there is two surfaces and they are in contact, there is a motion. When there is a motion, then there is a force of friction to resist the motion. So the force friction is something which resists the motion of the two objects. And again, we measure all of them in units of Newton. Now, there are two different kinds of friction forces. One is called static and the other one is kinetic. If the object is a static and it's not moving, you push it, but it's not moving. Technically, it doesn't move because there is a friction force called static friction force against it. The magnitude of this static friction force is equal to the amount of force you apply. You apply 10 Newton, it doesn't move, the friction is 10 Newtons. You apply 12 Newtons, the object doesn't move, so the static friction is 12. But there is a kinetic friction. That kinetic friction exists when the object is moving. So regardless of if you push or you don't push, if the object is moving and the surface are in contact, then whatever is the mass, the normal force to the surface, multiplied by that friction coefficient of the surface will give you the kinetic friction. You can calculate the static friction, but that static friction, you can only calculate the maximum static friction, not the from the normal force. So if you have a surface and the normal force is N, then you have friction static and friction kinetic. There is a maximum static friction, which is mu S times N. There is a friction kinetic, and that's mu K times N. But the static friction at any moment is equal to the force when A is equal to 0, when the object is not moving. And so, historically speaking, you apply a force, let's say this is the, how do we show it? Let's say it goes up, then it drops and remains constant. Let's say this is the external force you're applying, and the friction force can be measured in this way, that you apply the external force and the object doesn't move, and it would be equal to the friction as long as it's not moving. And this is, let's say, time. And then at some moment, the object starts moving at this point. And then after that, suddenly the force of friction drops down and reaches a balance, a constant value, where this constant value is equal to this value. Now, the maximum amount in this top can be calculated from the F friction maximum. Good? But as long as you are not moving, as long as the object is not moving, you can say that the static friction is equal to the force which you apply, whatever is the force you apply. Okay, so that's the first thing. And then we talked about Newton's law. Make sure you know that the inertia is the tendency of the object to resist change in its velocity. That's traditional definition for it. Newton's and technically the Newton's first law is about inertia. If the object has no acceleration, if there's no force exerted on an object, then object remains at rest or moves with a constant speed. So the state of matter object will remain at rest or in uniform motion if there is no external force acting on it. If there is an external force, then the object will not remains at rest or does not remains on a constant velocity. Which brings us to this point. If something is moving forward or backward, if something moves on a straight line but accelerates, speed up or slow down, that means there is a force applied on it. If the object is not on a straight line, even if its velocity, the magnitude of its velocity is constant, the speed is constant. If it's moving on a circle or a curved path, that means there is acceleration. Which brings us to this idea that the force, the external force, will create acceleration, which is change in the velocity. So when there is force, external force, then we will have changes in the acceleration. And then third Newton's law guarantees that for every action, there is a reaction. Action and reactions are exerted on two different objects, so they cannot cancel each other. So when you are sitting on a chair, these two forces, that the force that the earth is pulling you down, and so you go down, and then the force where the chair exerts on you as a normal force, both of them are exerted on the same object, so they can cancel out. So you're sitting on a chair, the two forces exerting on you, one is down, one is up. These are not action reaction. These are two forces acting on you, and they can cancel out. They are not subject to the third Newton's law. But the third Newton's law guarantees that if you are pulled down by the earth, then you are also pulling the earth up. That's the third Newton's law. Now, a lot of people make mistake. They think the action reaction means you hit someone and then someone hits you back. That's technically the action reaction, but it's different from when you hit the surface. You hit the surface hits you back. Now, these are exerted on two completely different objects. So this is Earth, this is you. The Earth is pulling you down. That's one force. One exerts on two. Then you are going to pull the Earth up. And the action reaction says these two, which are exerted on two different objects. The F12 is equal to F21. The magnitude is the same. And if you bring the vector into the case, then the direction would be opposite. So the negative sign guarantees that the directions are opposite. Good? Okay, so that's technically the third Newton's law. We're talking about gravity. We talked about the free fall. We talked about the terminal velocity. When there is a drag force, then the terminal velocity becomes important. And then gravitational strengths, right? So the acceleration of the gravity on the surface will be the force of gravity over the mass in that place. In this case, is technically the surface gravity is about like 10 or 9.8. We also talked about the friction. So, right, I already talked about it. Okay. Now, there are some fundamental things you have to know, or anyone should know about dealing with forces, the Newton's law. And the major part is drawing a free body diagram. Now, some free body diagrams are easy, some free body diagrams are complicated. Like when you have a system of objects, then drawing a free body diagram for them is complicated. Like if you have a surface with angle theta and you have an object like this, Well, free body diagram is easy to draw. Okay, so this is the mass. You will have an mg downward. You will have a normal force upward. And if you have friction, then you will have f of f upward. So you have to decide where is the coordinate system first, always. I can pick a coordinate system which is like this, x, y, or I can pick a coordinates which is parallel to the surface and perpendicular to the surface. Which one is better? Which one is easier? Now, a lot of times you have to go back and look at technically the direction in which the object is moving and how many forces you have on which coordinate system makes it easier. Now, in this surface, the object is moving down, let's say, with some acceleration in this direction. So it's much easier if I pick this one as an x. So in this case, at least I have only one component for the acceleration, and so it would be much easier. And so historically, we get rid of this kind of coordinate system. We don't use that. Okay, now in this case, I would say now I have a coordinate system, which is x and y. But remember, this is the x, is parallel to the surface, and y is perpendicular to the surface. That means I have an acceleration, which is in this direction. Now, normal to the surface is obviously normal to the surface. So it would be in the y direction. So that would be n. Friction is easy because it's to the left side, opposite to the motion. So that is the friction. But now what is hard is the force of gravity, which you have to identify this angle for it. Okay, so I'll draw this line. Now here's the thing. You have a surface and you have something perpendicular to it. Then you have another line, right? And then you have another line which is perpendicular to it. And the key is here. This is 90 degree. This is 90 degree. So when you have such things, the angle that you created between one of them and another one would be the same as the angle between this one and this one. So this angle is theta, then this angle should be theta. Good? Okay, so that means this one is theta. Now, if I rotate it, this is the vertical, and the angle between mg and the vertical is theta. So that means the angle between vertical and theta and the mg would be theta. And so that would be my free body diagram. So I have three forces and then one angle. Now, the hardest part is actually this part. If you draw the free body diagram, then everything else would be simple. And I'm expecting my students to always, at least during the course, follow this one. Now, you can do a lot of it in your head, but I insist students have to write it down like this. So first, they will say x direction. And then they will look into the x direction and say, how many forces I have? So I have F in the x direction, all of them. Add them together, and it would be the acceleration times mass in the x direction. Then you have the y direction. And then in the y direction, again, you will have the sum of all the forces in the y direction equal to m times acceleration in the y direction. And now you will see the choice of coordinate system. In the y direction, acceleration is 0. In the x direction, acceleration is just simply a. And then now the rest is easy. Now you look at your free body diagram, and you will say on the x direction, I have nothing to the right side, and then f of f to the left side, and this would be equal to m times a. On the y direction, I will have the normal force minus, I will have, oh, wait a second, I made a mistake, because I need to break this mg into two components. One component here, one component here. And so there is one component here, which is mg sine of theta, and there is one mg cosine of theta here. So I made a mistake here. There is a little tiny components to the right side. So that's mg sine of theta. And then here I have n minus mg cosine of theta, and it would be equal to m times 0, which is 0. Equal to 0. Now, this is easy to solve, so I would say n is equal to mg cosine theta. The reason this is useful is because f of f would be mu times n, so I can easily say that mu mg cosine theta would be the f of f, which I needed for the other one. And so I can take this one to the other side and say mg sine of theta minus mu mg cosine theta is equal to ma. Obviously, a is used in all of them, so I can cancel out. And that's it. Now I can solve this equation. So I have g sine of theta, g sine of theta, then I have minus mu g cosine theta minus mu g cosine theta, and it's equal to ma, and a is in the positive direction, so it's equal to a. That's it. If the acceleration is what we need, then you can solve it from this equation, right? If there is no friction, and you can test it always, that if friction is equal to 0, then g sine of theta would be equal to a. And we know that from the experiment. That's what Galileo did. So created the surface, tilted, and depending on how big was the theta, the acceleration changed. When theta was 0, the acceleration was 0. The object didn't actually fall. But when the angle was 90 degrees, then when theta was 90 degrees, then acceleration was exactly equal to g. And so it's consistent with our natural experience. Okay, so that's when you want to draw a free body diagram. Now, that's if you have only one object. What if you had more than one object? Let's say you had two objects. You have a surface, and you basically have one object here, and then you have one object holding it or causing it to move. So this has some amount of mass. So it has some mg. Let's just call it m1. This is object 1. This is object 2. And this one has m2g, right? Bring it down. Now, suppose the tensions are, suppose that the rope between the two objects, 1 and 2, is not stretching. That means this one, the rope is going to stretch upward, but it's not going to stretch, so it's going to hold the object 2. Then that tension goes here, then it goes around here, and it goes to the end. Whatever is this tension would be the same as this one, would be the same as this one, and would be the same as this one. So the tension would be the same, simply because the rope is not going to stretch. And so now I have two basically systems. I can say they are separate, but they are also connected. So for the object 1, then I would have a mass here. Then there would be an m1g downward. There will be a tension T to the right side. Let's say there are a little tiny friction to the left, right? F of 1. So I will have F of 1. And then you have, it's on the surface, so there will be a normal force upward. And so there will be a normal force upward, call it N1. So that would be the free body diagram for the object 1. But what about object 2? So for object 2, I would have an M2G going down. I will have a tension upward T. This one is not connected to the surface, so it's not pushing against the surface. So there's nothing to the left. If there was connected and there was friction, then this object is moving, let's say, down. If it was moving down, then there would be a friction upward. If it was connected to the surface. If it's not connected to the surface, then you can completely ignore the friction. Now you have two free body diagram, and now you can solve it. Again, you have to always separate the x direction from y direction. And so in X, and then also you have object 1 and 2. So for object 1, so here's what I have. So for object 1, I have in the X direction t minus f1. So I assume that this is a positive direction for X. And also, I want to consider that this is a positive direction for Y, upward. Okay, t minus f1, t, okay, let's say t1, and the t minus f1 is equal to some acceleration, m1 times acceleration for the object 1. And then I have vertical direction, n1 minus n1 minus m1g equal to, now, object 1 is fixed on the surface, so it's not going up, not going down, so its acceleration in the y direction is 0. It would be equal to 0. Why? Because a in the y direction is equal to 0. Because there's friction, so this N1 becomes M1G, and F1 would be mu times M1, so it becomes mu M1G. Now, you take this one, you replace it here, you will get T1 minus mu M1G equal to M1A. 1. Now, keep this as A1 because we need to explain why A1 is the same as A2. So, okay, so that's one equation, and A1 is not known, and T is not known. Then you go back here and you say, okay, now I have free body diagonal for object 2. This one also have, so let me just change my color. So then you have object 2. So in the x-axis, I have nothing, so there's no forces. So the sum of all the forces in the x direction, m times x in the, so x in the left side is 0, right side is 0. Good, perfect, nothing to actually worry about. But in the y-axis, in the y-axis, I have t minus m2g. So I have t minus m2g, and this would be equal to m2 times the acceleration of object 2. Good. Now, here's the thing. If the rope here is not going to stretch, these two objects connected together, although one of them goes down, the other one goes to the right, but because they are connected with a very solid rope, that means the acceleration for both of them should be the same. And so you conclude that technically you would say A1 is equal to A2 because rope is solid connection, rope. And so I can just get rid of this index. Index 1, 2 goes away and becomes the same A. And so when it's like that, then now I can solve it. I have two equations, two constants. So from one of them, I can calculate the t and replace it in the other one and calculate the a. So let's go from this one. I would calculate t from here. T becomes m2 a, oh, a plus g. Then take this one, put it on the top here. So m2. Oh, it was better if I keep it as m2a plus m2g. So it's m2a plus m2g. Then you have minus mu m1g equal to m1a. So m2a goes to the other side, will give you, okay, so let me just take it and go to another page. So let me just take this one, copy, go to the next page, put it down here, right? So, oh, there are too many unwanted things. Okay, so we have M2G, M2A, M2A plus M2G minus mu M1A. Okay, so I'll take this one to the other side. So I will end up with M2G minus mu M1G equal to M1A minus M2A. This will give me M1 minus M2 times A. And this one gives me, okay, I can take a factor of G. and this becomes m2 minus mu m1. So acceleration then simply becomes m2 minus mu m1 divided by m1 minus m2 times g. Now this could have been actually much harder if instead of having flat surface, I could have actually make it like this. No, could have given an angle. So this is horizontal, you could have had angle and then flat. Or you could have had even this one also some angle. So you had one object here, then you had one object here that connected through a tiny wheel, and then both of them, so this is the vertical axis, both of them have angle theta 1, theta 2. That would be actually far more exciting question. But anyhow, you can easily solve for the acceleration. And if you have the acceleration, you can go back here and then replace it into one of these two equations, for example, this one, and calculate in this one and calculate the t. Right? Now, what is important? The important part here is to show the work, the x direction, y direction, showing all the components, explaining why something is 0 or why it's not 0, and then do it for every free body diagram that you have. Good? What else? Yeah, I guess that's the most important thing to know in this chapter. Let me solve something a little more complicated. Actually, I'll give it to you. You solve it, right? So let's say you have an object on a surface, M1, and then you have another object called M2, and they are connected together, and this one is connected. And then you have another object called M3, and then you pull it with some force F upward, with some angle like 45 degrees. Let's say M1 is the same as M2 is the same as M3. Okay, that's one condition. Let's say each one of them has friction, and the frictions are the same, and it's equal to 0.3. And you want to know if the F is 10 Newton, and let's say this one, each one of them is 2 kilograms. You want to know how much is the acceleration. Okay, let's just calculate it. So the force is 10 Newton, and you have three objects, each one 2 kilograms, with a force 10 Newton at 45-degree angle. So what we want to do, we want to solve this question systematically. Now, if it's given in a test, a multiple choice test, then it's a different. You can just guess. I mean, just technically for a multiple choice, I would assume first of all that the friction is 0, and then if the friction is 0, then there will be only a component F cosine of 45 degree, and then I will have 3 mass of m1 multiplied by the acceleration. So this would give me the acceleration. Very simple, right? F cosine 45 divided by 3m1 gives me the acceleration. If there is no friction. If there is a little friction, then this little friction plus this little friction plus this little friction are going to be subtracted from this part. Now, there is only one problem. This normal would be a little different, and this last friction would be a little smaller. So, okay, I'll find the maximum reduced acceleration just by assuming that F3 is the same. And then from the test, I will guess which one is the correct answer. But If I want to solve this one, showing my work, then I will do it this way. Ready? Are you ready? Okay, so object one, I will have m1g downward, I will have a normal force upward, I will have a friction to the left, and I will have a tension to the right. That's for the object one. Then for the object two, I would have exactly the same, right? So I will have a tension to the right, I will have a friction 2 to the left, I will have m to g to the right, I will have n upward. But wait a second, here, this one feels t, but also from the left side, this object is going to apply t to it, which is the same amount of this t, right? So object two will also have another tension from the left side. Okay, that makes it complicated. So that's for the two. And then for the three, I have this object, m3g is downward. I will have a friction, 3 to the left. Then I will have a force F with some angle theta to the right, which gives me two components, F cosine theta, F sine theta, and then I will have, as usual, a normal force, which is upward. Okay, now I want to go back to this. This is 3 to object 2. Look at the object 2. Object 2 is pulled from one side and it's pulled from the other side. So there's two t's involved in it. Assuming that all objects are moving to the right side, then the frictions are all to the left side. Okay, so y directions for all three cases. Okay, y direction, y direction. What do I have? I have n minus m1g equal to 0. Here I have n minus m2g equal to 0. And here I have n plus f sine of theta minus m3g equal to 0. From here, I will conclude that n1, if you like, is m1g. Call this 2, 1, and this 3. n1, 2, and 3. So this n2 becomes m2g. This n3 becomes m3g minus f sine of theta. The reason I need this is because f1 is mu n1, which in this case becomes mu m1g. F2 would be mu n2, which becomes mu m2g. And F3 would be mu n3, which is mu times m3g minus f sine of theta. So that's the y components. So I resolved that. I need to use F1 later on. And then I go to x components for all three of them. So x component or x direction, x direction, x direction, x direction. Okay, so yeah, in the x direction, for one, I have t minus f1, t1 or t, let's just call them t1 for now. So call this one t1, call this one t2. This one would be the same as t1. And then this one, there's a tension to the rope. I forgot to write it. That's t3, right? Because it's connected to this rope. So there's a t3 here. I give them different names. So technically, we can find how much is that. This one, I don't know it. So let's just call it t prime 1. And then we will find if t prime 1 should be equal to t1. Okay, so here I have for the t1 minus f1. So I have t1 minus f1 is equal to m1 times a1. Then I go to this one, I have T2 minus T prime 1 and F2. So I have T2 minus T prime 1 minus F2 is equal to M2 times A2. And then for the last one, I have F cosine of theta, F cosine of theta minus, I have T3 and F3 minus T3 minus F3 is equal to M3 multiplied by A3. Now, if the rope is connected and it's not breaking at all, that means all these three objects are moving together. Good? So the acceleration should be the same, because acceleration is just technically the rate of change of the velocity. And the velocity is the rate of change of the position, and the position is changing together. So the acceleration is the same. So I can conclude from here that rope is solid. So A1 is equal to A2 is equal to A3. That's one assumption here. The second assumption here is this one is T1 and this one is T prime 1. If the rope here is solid, the left side of the rope and the right side of the rope should have the same tension. Otherwise, it's going to break, right? It's going to stretch. So T1 is the same as T prime 1. What else? The same is true here, actually. This side and this side should be the same. So whatever was this T2 and this T3, it should be the same. Otherwise, it's going to break. Okay, so from here also I can conclude that T2 is the same as T3. Okay, so T3 and T2 are acting on this rope. To avoid breaking the rope, these two should be exactly equal. And T1 prime and T1 should be the same, so the rope it doesn't break. Okay, now I'm going to go ahead and replace them. So I don't know if T2 should be equal to T1. Okay, so here, T2 and T1, there's no reason for them to be equal. Why? There's no reason to assume that. So you keep it different. Okay, so let's just replace this one and replace the frictions. So F1 was mu m1g. Okay, so I'm going to replace it. What happened? So T1 minus mu m1g is equal to m1a, and a is the same, so I'm going to replace it with a for all of them. And then we have T2 here minus T prime 1 is T1 minus, and F2 is mu m2g, so mu m2g is equal to m2a. And the last one is F cosine of theta, minus T3 and T2 are the same, so I'm going to replace it with T2. So I have only one parameters. And then minus F3 is mu times M3G minus, and that is also a minus, so it's plus mu F sine of theta, and it would be equal to M3A. So how many unknown parameters I have? Mu is given, G is given, M1, M2, M3 is given, 1, 2, 3 is given. Actually, I said it's the same, so I can just get rid of this 1 from the M's. So the M's are the same, and just get rid of it. It's one level for easy. So I will have 1 M. And what else is given? Mu is given, M is given, G is given. That's it. Now I have how many equations? I have three equations, and I have T1, T2, and A, unknown, 3 variables. So I can solve it. Okay? So it's very likely that this has one solution. How do I solve it? One easy way is to add this equation to this equation then T1 cancels T1. You will end up T2 and mu mg and mu mg. That's 2 mu mg. And on the right side, you will have 2 ma. So you will end up, let me just write it down. So I have T1 minus mu mg equal to ma. And then I have T2 minus T1, T2 minus T1 minus mu mg equal to ma again. Just add them together, add them. And so what you would get is T2, this minus T1 cancels T1, minus 2 mu mg equal to 2 ma. That's a new equation, has only T2 and A2. And now I have this equation. Okay, so let me just write it down. So I have f cosine of theta plus mu f sine of theta minus T2 minus mu mg minus T2 minus mu mg equal to ma. I can calculate actually T2 from here. I can say T2 is equal to 2ma minus 2mg. Then take this one and replace it here. So I will get f cosine theta plus mu f sine of theta minus 2ma minus 2mg minus mu mg equal to ma. This goes here. That becomes 3ma. This, I forgot a mu here. This 2 and this one becomes minus 3. So minus 3m minus 3 mu mg is equal to ma. And then we have f cosine theta plus mu f sine of theta. So what is acceleration? Everything divided by 3m. So you will end up with f cosine theta plus mu f sine of theta divided by 3m. And this becomes 3m cancels, that's mu g minus mu g is equal to a. That would be the acceleration. Now, if I have the numbers, I said F is 10 newtons, mu is 0.3, m is 2 kilogram, and theta is 45 degrees. So you can now replace it here, and you will get 10 times root square 2 by 2 plus 0.3 times 10 times root square 2 by 2 divided by 3 times 2 minus 0.3 times 10 equal to, that's 5, that's 5, that's 5 times this is 1.5. So I will end up with 5 plus 1.5, that's 6.6, 6.5 root square 2 divided by 6, right? 5 plus 1.6, and then minus 3. That would be the acceleration. How much is that? Well, I don't know. So 6 root squared, no, 6.5 times root square 2, then divided by everything divided by 6, then minus 3. Is that correct? Did I do it correctly? Mu 0.3 times 10 minus 3g, 3m, right, mu f, right. So here's the thing. We get a equal to minus 1.4. What does it mean, minus? The force was to the right side. That means acceleration cannot be negative in this case. That means it's not going to move. So that means the F is not enough. It's going to stop. So technically FA would be 0. It's not going to accelerate. 10 Newton is not going to do the work. You need much bigger. So if it was, let's say, 20, then possibly this would have worked. So let me just go back here to this equation and say, if F was 20, then you would have 20, what happened? 20 times root square 2 divided by 2. And that's one part. Then you have plus 0.3 times the same, 20 times root square 2 divided by 2. That's one bracket. And then you can have one big bracket here divided by 3 times 2 because of the math minus 0.3 times 10. And yes, then it would give you a positive number. So 10 Newton is not enough for this object to move. So if you apply 10 Newton, it's not going to do the job because the friction, the objects are too heavy. If there was no friction, now let's see if there is no friction. Does that work? So if there's no friction, means mu is 0. What do you think is going to happen with even 10 newtons? Then you will have, this one would be 0, this part would be 0, so you will end up with F cosine of theta divided by 3m is equal to A. And yes, this would be 10 times root square 2 divided by 2 divided by 6. That gives you 5 by 6 root square 2. And it is a positive acceleration. So any questions? No? Let me stop recording.